Hello. So here's the gray code to hex converter, and essentially the hex is displayed through a 7-segment display. It is done through k-mapping to minimize the number of logic chips required significantly. And there's also a rotary encoder that toggles from 0 to F or 0 to 15 in gray code. Okay, so I'm just going to show how to fill in one K-map first. So this is the A segment, the K-map for the A segment. So here's first the conversion between decimal and gray code. So we want to convert the gray code to decimal through a 7-segment display. So we identify for which digits do we want segment A to be on. For example, when DCBA are all 0, which is what this box is, so that is the decimal 0. So on the 7-segment display, we want A, F, E, D, C, and B to be on. Thus, in that case, A has to be on, so we put a 1 in that box. So next one. Here, all are low, but A is high. So if we look at the table, that is a 1 in decimal. So looking at the 7-segment display, for a 1, we only need a B and a C, so A needs to be low, thus a 0 in that box. I've added in these small numbers here, which are just what each box signifies in hex from 0 to F, so it's easier to identify whether an A is required or not for these boxes. So now I'm going to fill in the rest of the boxes with this logic. Now, once the ones and zeros are found, they must be grouped for simplification through the K-map process. So groups must be rectangular, horizontal, or vertical, and contain 1, 2, 4, or 8 cells, so powers of 2. They must also be as large as possible and include every one, even if this means overlapping groups. So in this case, first of all, a K-map, it behaves like a cylinder, so the corners wrap around. Thus, they can be a group as well. As a result, the purple group is formed. In those 4 boxes, the B can be 0 or 1 in the top 2, and then D can be 0 or 1 when you compare the top and the bottom ones. So that means that only C prime and A prime are the ones that are not changing. So those are the only ones that actually matter. So that means that those 4 can be simplified as just A prime, C prime. For now, the next one, the orange group, it contains either D/D prime or C/C prime. So that means only B prime and A prime, in this case, if we look at the table, have to be true for it to work. So as a result, this group results in a logic of A prime, B prime. Now the green group, it contains either B/B prime or D/D prime, meaning only A and C must be true. And as a result, this group results in a logic of AC. The red group, it contains either A/A prime or C/C prime, meaning only B prime and D must be true. As a result, this group results in a logic of B prime D. Finally, the black group contains either A/A prime, meaning B, D prime, and C prime must be true in this case, if we look at the black group that's being circled. As a result, this group results in a logic of B, C prime, D prime. The result must be a sum of products. So that gives the final equation A prime and C prime, or A prime and B prime, or A and C, or B prime and D, or B and C prime and D prime. So from this, we can actually do some factoring as well, just to simplify the number of gates required. So the A prime and C prime, or A prime and B prime, that can be simplified by factoring out the A prime. So we get that. So this gives us the final sum of products. And from this, we can see that we require six NOT gates, 5 AND gates, and 4 OR gates. Now the same process is done with all the other letters from A to G in the 7-segment display. Now, when wiring, based off of the logic for each segment, I can toggle the 7-segment display accordingly through my gray code encoder. As this is my final project as an ace in hardware, I also want to thank Mr. Darcy for all the support he has provided and the effort he has put into this course to make it as enjoyable and as comprehensive as it is. Every single one of us truly appreciates it. Thank you so much, sir, for a great 3 years, and I hope to post more videos about my future non-ACES related projects. Thanks for watching.